Hello, in this lecture I am going to continue on the discussion related to weak convergence, the concept of weak convergence or convergence in law. So far we have understood what is the basic idea behind weak convergence and what is the formal definition, and in the last class I have introduced another equivalent definition of weak convergence. Today we are going to see a continuation of that. I am going to introduce 5 equivalent statements, each of which can serve as a definition of weak convergence. So I have got a sequence of random variables, and x is a random variable on the same space. All these random variables are same space. So we want to define a convergence of xn to x, convergence in law, or weak convergence as n tends to infinity. So to recap quickly, this is the definition that we learned in the last class, that expectation of gxn converges to expectation of gx for every real valued bounded continuous function g, right? In fact, this was used to prove that convergence in probability implies weak convergence, if you remember. And here I have not included the first definition because that is something I am taking as the basic definition, that xn is a sequence of real valued random variable converging weakly to x. That means fn, the corresponding distribution function fny, converges to fy at every continuity point of the letter, that is that of x, f. So in the last class we have seen that these two definitions are equivalent. So now let us take expectation of gxn converging to expectation of gx for every bounded continuous function g as the basic definition. So this naturally leads to the second condition, second statement, that the characteristic function. So if you see what is expectation of itxn, this is really the characteristic function of xn. So let me introduce a Greek symbol, Greek math, phi xn, right? Script phi xn. So let me call it phi nt. Phi nt equal to expectation of itxn converging to itx, that is equal to phi t for every real number t. So what I am defining now is that we can also define weak convergence in terms of pointwise convergence of the characteristic functions. Now 1 implies 2, that is obvious. Why? Because what is phi t? Phi nt, that will be expectation of two parts. It has a real part and an imaginary part. One real part is expectation of cos t xn plus I sin tx, and cos and sin both are bounded continuous functions. So 1 implies 2, that will follow immediately. Okay, but the fact that 2 implies 1, that is not very easy to prove. Okay, so anyway, at least we do see that how 1 implies 2. So this is in fact one of the main workhorse when we want to prove weak convergence. We often prove that phi nt converges to phi t, as we shall see in the case of central limit theorem. And then there is a third case, that is, if we can prove that fny is converging to fy as n tends to infinity, where fn is the density probability mass function or density function of xn, and it is converging to the density function or the mass function of x, pointwise convergence, then also this means that xn is converging weakly to x. So again, this is a result that is useful when we prove that under the condition that when n tends to infinity, p tends to 0, such that np converges to lambda, the binomial distribution converges weakly to Poisson lambda distribution. So here basically what you see, the fny is the probability mass function of the binomial distribution that converges to fy, where fy is the probability mass function of the Poisson distribution. So there we do not go for the characteristic function straight away. It is because that is convenient there. So with the purpose of having this equivalent definition is that we can apply whatever is convenient where. So these two are frequently used to prove convergence of sequences of random variable, real valued random variables in weak sense. And then there are 4 and 5. These are more of academic interest for you at this stage. So basically what this says is that if O is any open set, take any arbitrary open set of real numbers, probability that xn is in O, lim_inf of that is greater than equal to probability of x in O. So this has to be true for every open set, and from there, just since probability of A complement is 1 minus of probability of A, you get the other part. So for closed sets, the inequality will reverse and lim_inf will get replaced by lim_sub. These are also handy, but at this stage you just know them. Mainly if you can understand this definition, number 1, and then 2 and 3, these 3 should be suffice for this course. So now let us, we have, so now the collection of these statements actually to 2 and 3 I have introduced here, but in general 1, 4, 5 and then there is another statement that I have not included here. So they are together known as the Portman Two Theorem. So these are the equivalent ways of proving weak convergence or defining weak convergence, and this statement number 1, that is that you can think of the most easy and general way of defining weak convergence, not only for sequence of real valued random variables but for random variables that take value in, say, complex valued random variables or RD valued random variables, or even random variables which take whose range is a function space. For example, random variables which take values in C01. So when we do, your course is very basic. Here we are concerned about real valued random variables, but as you progress, we talk about random variables that are mapping from a probability space to Rn or infinite dimensional spaces. So those are, that is a subject called stochastic process. So let me not get into all that. But the point is that this statement number 1 is even handy there. So as I said, but let us appreciate 2 and 3. So what if you can prove phi n t is converging to phi t for every real number t, then you can you have actually proved the weak convergence of xn to x. So in this context, so let us go back to this result which I have earlier mentioned. Suppose I have got a sequence of x1, x2, xn IID random variable, square integrable or finite variance. So I can say basically xi's have finite variance, and to make life simple, let us assume that mean is 0. Okay, if mean is not 0, you can just subtract the mean and make them 0. So now define a new sequence of random variable yn, which is 1 by root over n times x1 plus x2 plus xn, or yn you can easily see this is root n times x bar, where x bar is the mean of x1, x2, xn. So now this is an exercise that we have done earlier. So can you find the characteristic function? So what will be the phi n t? So the phi n t here, so in this case the phi n will be the characteristic function of n. So the characteristic function, so let me specify, space of characteristic function of yn is phi n t, expectation of yn, and then using the properties of characteristic function that you know, that would be phi t by root n raised to the power n, because x1, x2, xn's are IID. Then this is slightly advanced. This is something you may not have done in the characteristic function, that if a random variable has a kth order absolute moment, then you can have a Taylor series type expansion of the characteristic function in an open neighborhood of 0. So for fixed t, as you make n large, so you t by n root n goes close to 0. So by that result, since we are assuming that the variance is finite, so I can have a Taylor series type expansion of this characteristic function. And so the first term, if you look into the note related to the moment generating function, you will see a expansion like that, the moment generating function can be written as 1 plus t into the mean expectation of x plus then summation of t to the power k by k factorial into expectation of x to the power k. So this is a similar expansion to that. Remember, here mean is 0, so and you know, when the moment generating function is there, so the moment generating characteristic function is similar to moment generating function, just replace t by it. So we get a similar expansion here, and then you see the mean is 0, so the t by root n term is not there, but the second is sigma square into t square by 2, and t by root n would become t square by n, and then the remainder term is a higher order power of n. So then this is what it is, and then you have to take you can show that this converges to e to the power minus sigma square by sigma square into t square by 2 as n tends to infinity. Now this involves slightly it's slightly mathematical because of a simple reason. I tell you, we generally take a logarithm and then n comes out and then we usually treat it. So now here what happens is that see, phi n is a complex valued function, so the logarithm that you are taking is going to be a complex logarithm. Okay, so then actually we take the principal branch and do the analysis. So let me not get into all this. The point is that you can show. Now you can of course make life little bit easy if you assume that these xi's are symmetric. Then you know that if xi's are symmetric, although there is no such restriction in the central limit theorem or in this problem. So if you assume that these xi's are symmetric, then these phi nt's will be, this phi will be real valued function, then the usual natural logarithm will work. So anyhow, so then you take n tends to infinity and then you get this result. Then that phi nt is converging pointwise to e to the power minus sigma square t square by 2. So that is the result I wanted to show, because now you see what this statement 2 is saying, that if phi nt is converging to a characteristic function phi t of some known probability distribution, then for every t, then you can say xn is converging weakly to x. So now here what we show is that phi nt, that is the characteristic function of this yn, is converging pointwise to, this is the characteristic function of n0 sigma square, where sigma square is the variance. So therefore you can from the equivalent definition 2 we get this is converging weakly to, or converging in law to a normally distributed random variable, or weakly to n0 sigma square. So this result is known as the central limit theorem, and this result holds only when the variance is finite. So we need the finiteness of variance in order to have a Taylor series expansion of the characteristic function up to this second order as a second order polynomial in T. Otherwise you don't have this expansion, and in fact this is a necessary condition that we will show in the next example, that if you drop this condition, then the CLT does not hold. So for example, suppose I have x1, x2, xn IID Cauchy random variable, that is students T with 1 degree of freedom, and I want you to find out the characteristic function of this 1 by n summation of xi's. So here I am giving you some input that the characteristic function of the Cauchy distribution is e to the power minus mod t. How this is, that is another story. So this is I am giving you. Then from what you know, you can easily figure out that the characteristic function of then this 1 by n summation of xi will be phi t by n raised to the power n. So it will be e to the power minus t. So these zns, all of them follow Cauchy distribution again. So zns converge indicates to the Cauchy distribution again. So root n into Zn does not converge in any sense. So therefore